Kia ora koutou. This video is for Ben, Tosef and Snehal, but also for any 13 MCA students who are retaking AS and for 12 MCA later on in the year. What I've done in here is looked at some of the questions that we should already be able to do using trigonometry. So if Ben, Tosef and Snehal, if you're watching this, I'm not going completely in order in that little booklet. I've just picked out the trig ones. I'll do the coordinate geometry ones later on. I want to look at the two different types of questions that often come up in the AS exams on trig. So the first one we've got here is a classic where we have to first of all prove an identity, and then we have to use what we've done in that part to solve an equation. And here it's for a domain between 0 and 360 degrees. And that's a really common pattern type. And the skills we need in there are how to do proofs and some basic trig identities. The main one for AS being the Pythagoras identity. Okay, so that's worth 6 marks. Remember, the total exam is worth 75 marks for pure 1. The second one is often more challenging until you get used to what you need. And this uses really basic trig from right angle triangles. So it's often going to use so katoa somewhere in there. We're going to hunt for a right angle triangle. And then it's going to use things like the area of a sector and the length of an arc. So this is the arc length formula, and the area of a sector formula is half r squared theta. And these things come up over and over. Right, okay, so I'm going to get into it now and start with this proof one. The first thing that you need to know is that when I'm doing a proof, I don't work with both sides at once. I start on one side, and here I'm going to start on the left-hand side, and then I do stuff to one side until I get to the second side. Right, so we look at the question and we see an equal sign, but when we go to start it off, we go like this. Oh, where's my pen gone? Sorry if you hear kitchen noises in the background. It is dinner time here. Right, so the left-hand side, I've got sine theta plus cos theta times 1 minus sine theta cos theta. And that's what I'm starting with. And I want to end up with sine cubed theta plus cos cubed theta. Sorry, that's the kitchen noises. Right, but I'm not going to write that out. Okay, what I'm going to do instead is I'm going to do the obvious first thing here, which is to expand out these brackets. Right, so if we do that, I'll just get rid of this mess over here from when my laptop battery ran out. This is what I get. First of all, I get sine theta plus cos theta. That's from the 1 times both of those. And then I'm going to get minus sine squared theta cos squared theta minus sine theta cos squared theta. So I'm looking at that now and I'm thinking, well, I need to somehow get in there sine cubed theta. There's only really one identity that we use a lot in AS, and that's the identity that says that sine squared theta plus cos squared theta is equal to 1. So if I see a cos squared theta, now something's gone wrong in there, hang on. That should not be a squared, that should just be a cos. Let's just fix that one up. So where I see the sine squared theta, I'm going to replace this. And I'm going to replace it with sine squared is equal to 1 minus cos squared. And where I see the cos squared term, I'm going to replace it with 1 minus sine squared. Now, you don't need to write all of that out. You're just going to do it in the working for the proof. So that's my next step now. So I'm just going to erase that because we want our proof to flow logically from one line to the next. So we've got sine theta plus cos theta minus 1 minus cos squared theta times cos theta minus sine theta times 1 minus sine squared theta. Now we're going to expand all of that out and we're going to hope that some stuff disappears. So sine theta plus cos theta minus cos theta plus cos cubed theta. So that's looking pretty good. Minus sine theta plus sine cubed theta. And look what's happening. We've got sine theta, take away sine theta. And then we've got cos theta, take away cos theta. So that leaves me with cos cubed theta plus sine cubed theta, which is the right-hand side as required. That's the first part of that question done. Now, in the second part of that question, we have to use this to solve this. So we'll just start out by saying that this sine theta plus cos theta into 1 minus sine theta cos theta is equal to sine cubed theta plus cos cubed theta. And now we're told that that is equal to 3 cos cubed theta. So this is the equation that we're working with, right? So this is completely different logically than the proof. We're saying that these two sides are the same, and now we have to find the theta value for which that statement is true. Cleaning it up, we get sine cubed theta is equal to 2 cos cubed theta. Dividing both sides through by cos cubed theta gives me sine cubed theta over cos cubed theta is equal to 2. Now I've done that because sine theta divided by cos theta is equal to tan theta. So here, what I've got now is tan cubed of theta is equal to 2. Remember that what this is equal to, even though we write it with the 3 here, is that this is tan theta cubed. But we never write it like that, so there's a really strong convention that we write it as tan cubed theta. The next thing that I'm going to do is I'm going to take the cube root of both sides. So now we have tan theta is equal to the cube root of 2, and I'm going to chuck that into my calculator, and that will give me my first solution, which is 51.6 degrees. So that's the first one. It's always worth drawing a graph when you're doing a trig equation in AS, because we need to find all of the solutions between 0 and 360 degrees. So let's just have a look at what we've got. Well, we want the cube root of 2. Now, I completely forgot to write down what that number is, but it's 1 point something. And so I'm looking on here, and that 51.6 is the first solution I've found here. But there's going to be another one, another 180 degrees over. So that second solution will be 231.6 degrees. Remember that the tan function is the easiest one to work with for solving equations because it just repeats every 180 degrees. Okay, so that's already 7 minutes just on that first question, but hopefully I've gone through that slowly enough. Please send me an email if you're not sure about it yet. And again, I'm sorry for the noises of the pressure cooker in the background, but there you go. Okay, let's look at this next one. Now, this looks really, really daunting, I think, when you first see it. But you're going to find that there are patterns that come up all the time with these problems. So just try not to freak out. Right, we've got a diagram, and we've got a circle, and we're told that the radius is r. So we're just really slowly reading through the information. The points A and B are on the circle, yep, and AT is a tangent to the circle. So we know from back in, I guess, sort of level 1 geometry, that when the tangent meets the circle, the tangent is perpendicular to the radius. And that means that I can draw in a right angle in that triangle. We also know that this angle is theta, and the OBT is a straight line. Yeah, well, that's kind of obvious. We have to first of all express the area of the shaded region in terms of r and theta. So the shaded region is going to be the area of the triangle minus the area of the sector. So we're going to write some words for this. So the shaded region is equal to the triangle OAT, minus the sector, and I've just written that as AOB. The area of the triangle is half times the base times the height, right? So I'll just draw that triangle out there. There's A, there's O, and this is length R, and that's T. The angle theta is in here. So from baby trig, we can do so katoa on this. We want to figure out what AT is. So A is the opposite side, and R is the adjacent side. That means that we can say tan theta is equal to AT divided by R. AT is equal to R tan theta. Okay. So the area of the triangle can be rewritten I'll just get rid of those, as 1/2 times r from here times r tan theta. And I've still got to do the area of the segment. But the area of the segment is really easy because it's just sitting in here. The angle is theta, so it's -1/2 of r squared theta. So that equals 1/2 r squared times tan theta minus theta. And I think that's all we had to do with this question. Yeah, oh, we just had to express the area of the shaded region in terms of r and theta. So looking at that one, I've factorized it here, but actually you would get a tick just for getting down to there, but this looks nicer. The next step is to find the perimeter of the shaded region for a specific case when r is 3 and theta is equal to 1.2. So the perimeter of the shaded region has got 3 bits. It's got AT, BT, and that arc length AB. AB plus AT plus BT. So for AB, we have S equals R theta. And for AT, we've got R tan theta. Right, now for BT, it's going to be that whole length minus the radius. Using my basic trig again, we get cos theta is equal to R, so the adjacent side over the hypotenuse over OT. So OT is equal to R over cos theta. That means that BT is going to be R over cos theta, take away the radius. Now, I've done that for a general case. All we have to do now is to add those up and substitute these values in. Okay, so the perimeter here is going to be R times theta, so 3 times 1.2, plus for AT, we've got 3 tan 1.2, plus 3 over cos of 1.2, take away 3. And when I add all of that together, I should get 16.60 units. Okay, so there you go. That's the first 2 questions done. I guarantee that other questions you do this year with similar patterns are not going to feel as weird and difficult as those first couple. So just hang in there and make sure that you've written this up nicely for your own revision. If you've got any questions on that, guys, just send me an email, and that goes whether you're Ben, Tosif and Snehal or anyone else from Cole who's doing AS stuff. Thanks for watching.